Hello, good people. Welcome to Cosmology Talks. This video is part of the CAMELS series of videos on this channel. CAMELS is a group who have applied machine learning to cosmology. So in this particular video, there won't be an intro to CAMELS. So if you're unfamiliar with CAMELS, you should go and watch the relevant video, which will hopefully be being suggested on the screen at the moment, or is at least in the description. This particular one is a really interesting one that is attempting to get constraints on cosmology from a single galaxy. So it's not full constraints on all lambda CDM parameters of interest, but just omega matter. But even that is very interesting by looking within the CAMELS simulations and looking at individual galaxies and the properties of the individual galaxies. So there's quite a few properties an individual galaxy will have, but individual properties, they're able to get constraints on omega matter. This isn't robust to changes in the hydrodynamical simulation method, but it is super promising. And at the very least, it's indicating an observational difference between different methods of adding hydrodynamics to cosmological simulations. So enjoy. Welcome back to Cosmology Talks, Paco. Do you want to start by telling us briefly about your work?
So this is a little bit of a crazy idea that we have been exploring. This is something I have done in collaboration with Jupiter Dean, Shai Genel, Stephanie Tonensen, Valentina Latorre, David Spergel, Roman Tessier, Inli, Caroline Heneka, Pablo Lesmos, Daniel Agnes Alcázar, and Daisuke Nagai. The main idea here is, is like, can we do cosmology with one single galaxy? That's basically what we were trying to answer.
Right. So this is where the call ends, and I realize I've made a terrible mistake. Who is this crackpot? So what questions were you trying to answer with this, other than can we do cosmology with one galaxy, and why are these questions important to solve?
I mean, in reality, to be honest, we were not really trying to answer any question here. This was more like kind of a exploratory work. To be honest, I never thought that this would work. My idea originally was to use the minimum number of galaxies, such as you can do cosmology, because, I know things like the stellar mass function might be sensitive to the way that, you change omega matter or sigma 8. But I started saying, okay, let's put this to the limit. Let's see what happened with one single galaxy. And actually it works. So yeah, it was a bit surprising.
Let's get into the details then. What did you find with one galaxy? Got the full initial inflationary power spectrum. We know the model of inflation, how it reheated.
No, not yet. So basically what we did was to take simulation from CAMELS. So in CAMELS, let's say that you take one simulation, and this simulation will have a given cosmological value, knowing omega matter and sigma 8, and also these 4 astrophysical parameters. And there will be galaxies inside the simulation, right? There will be some dwarf galaxies, there will be some massive galaxies, there will be spiral, there will be elliptical, all kind of galaxies. And we took all the galaxies from one simulation, but also, from different simulations, like I think 800 of them. And every simulation, as you know, has a different cosmology and also a different astrophysics. And then what we do is the following, is that we take a single galaxy of a random simulation, let's say.
And you pick this galaxy just completely randomly. It's not like the most massive or the most something else.
No, completely randomly. And for every galaxy, we will have a set of internal properties, like for instance, the gas mass, the stellar mass, the black hole mass, the total mass, in this case also compressing the subhalo mass, a bunch of different internal properties of galaxies.
And are these all things that are kind of in principle observable, or are they sort of simulation specific? Or?
Most of them, but not all of them. For instance, this is the total mass of the subhalo. So this is not really observable, but we can come back to this later. You will see that actually for this thing, most of the things are pretty much observable.
Well, didn't Pablo, your CAMELS collaborator, give a talk on how to measure M total using observable stuff? So in principle, it's observable.
That's true. That's a good point. So basically, you take this random galaxy, you consider all these properties, and then you put this into a neural network. And the neural network is basically trained to predict all these quantities. Like for instance, the value of omega matter, the error on omega matter, the value of sigma 8, the error on sigma 8, and the same thing for these astrophysical parameters. And once the network is trained with a lot of galaxies, what you do is to test it, of course. So we have been basically training the network using galaxies from these 800 simulations, and now we take individual galaxies from simulations that are in the test set. So the network has never seen these simulations. And this simulation has a different cosmology, and a different astrophysics than the simulation that we have used to train the network. And this is what we get. So for instance, consider this point. This point is a single galaxy. This is a single galaxy that is coming from a simulation where the true value of omega matter is like 0.26, something like that. And then this galaxy will have like 17 properties. So you put these properties into the neural network that has been already trained, and the network is telling you that the value of omega matter is like, let's say, 0.2 with this error bar.
And you deliberately pick the worst data point, but like on the whole, it looks pretty impressive.
And you can see that the closer that you are to this black line, it means that it's working. So these are different galaxies. Let me emphasize, every point here is a single galaxy with a different cosmology, a different astrophysics, and this works. You can see that you are able to predict the value of omega matter.
I automatically want to ask, how correlated are these error bars? Because if these are independent data points, because they're independent galaxies, but maybe the uncertainty is correlated. But if these were independent data points, you'd have like a hyper-precise measurement of omega matter, right? Like sub-10% probably.
That's a very good point, Sean. So the thing is that these are coming from different simulation. Every galaxy here is for a different simulation. So in this case, I'm pretty sure, the error bar should be uncorrelated.
Well, these would be when we make an observation. It's one simulation. I mean, it's not a simulation. Well, some people think it is, but it probably isn't.
Exactly. So in that case, I cannot really tell you if the error bars are uncorrelated or not. So something that we would like to do in the future is, what about cosmology with 2 galaxies, 3 galaxies? Do this improve? I will expect so, but as you say, maybe the error bars are correlated, so maybe you don't gain that much. But we don't know yet. And you can do the same thing for other parameters. So for instance, for sigma, this doesn't work. You can see that the neural network is only predicting the mean value that we have in all the simulations with a large error bar. So you can see that it's not really working. The network is able to say something about this supernova parameter that we have, but for the other parameters, it's not really able to say anything. But for omega matter, seems to be working. Another question is like, maybe this happened by chance. Maybe we pick up, and this were only for some particular galaxies. Maybe there are some points that are a little bit odd. Does this work really for all galaxies, or is this really for some of them in particular? So this is what we did. So for instance, take a look at this panel here in the bottom. These are 150 galaxies coming from the very same simulation. So all these galaxies have the same value of omega matter, that is this black line, 0.45, something like that. And every point here is a different galaxy. The color just indicates the stellar mass of the galaxy. So you can see that this works for all galaxies, for all of them.
Am I seeing a bias towards smaller values here?
There is a little bit of a systematic bias, as you described, and that's true. But within the error bars, at least for one galaxy, we're fine.
That's true. Yeah. Actually, this does suggest the answer to my question from before of whether they're correlated. Like this might not be a bias. This just might be a systematic error.
Exactly. That's a very good point. Yeah, and we are not super sure what is this, but yeah, we have definitely there is in some cases a systematic bias. This is for a different simulation where the value of omega matter is 0.31, and you can see that still it works for all the galaxies. And this is if you take a value of omega matter much lower, like 0.15. So this is really working for all galaxies. It doesn't really matter what the stellar mass, for instance, in this case, you have. So, we got this result, like, to be honest, months ago. It's very cool, but, if you don't understand anything, it's maybe, we're maybe not physicists, no, at the end of the day. So, it took us a little bit of time, but at the end, we were able, more or less, we believe, to come out with a set of variables that are really important. What are the galaxy properties that are really responsible for this result? And basically what we come out is that the variable that are important is the stellar mass, the maximum circular velocity, the stellar metallicity, the stellar radius, and then for illustrious TNG we have the K-band, and for Simba in this case is the radius where the maximum circular velocity happens.
Okay, those seem like very different parameters, but all right.
Yes, exactly. And to be honest, we also are not really sure why is that. And just looking at these properties, to be honest, I also don't really understand much. What is really going on here? So then what we did was the following exercise. we took randomly 100 simulations from the 1000 that we have for Illustris and the 1000 from Simba. And then for each simulation, we took randomly also 100 galaxies. And then for every galaxy, we plot here the maximum circular velocity versus the stellar mass. So every point here is a galaxy, and this is like the maximum circular velocity, the stellar mass. And what we're doing is color coding the code according to sigma 8. So you cannot, I guess, at least myself, I cannot really see anything here. There is no pattern. But what happens if you color code these galaxies according to omega matter? Then what you get is this. And now there is a very clear pattern here. The pattern is the following, is that for a fixed stellar mass, let's take for instance this 10 to the 10, what happens is that as you increase the maximum circular velocity of the galaxy, the value of omega matter is also increasing. So what we believe is going on here is that as we increase the value of omega matter in the universe, there will be more dark matter around. And you will expect that galaxies will have a larger content of dark matter. There will be more dark matter in galaxies. So basically, if there is more dark matter in the galaxies, then the gravitational potential well you will expect to be deeper, and then the maximum circular velocity, which is basically just the square root of Gn over r. Basically, this will also be larger. So this is our explanation that when you increase the value of omega matter, you are really doing something physically different to galaxies, to, for instance, what a supernova feedback will do, and agent feedback. You can see that there is, of course, some scatter here. This is because all the simulations have different values of omega matter, but also different astrophysical models. So somehow, maybe galaxy properties will be segregated when you look at them as a function of omega matter. So, if you try to even plot the results in 3D, so, here we're plotting the stellar mass versus the maximum circular velocity, and this is the stellar metallicity. You can also see that galaxies are segregated when you consider the value of omega matter. And, we believe that, if we were able to maybe look at this in 17 dimensions, galaxies will be even more segregated. So we believe that this is, at the end of the day, what the neural network is really learning, that physically increasing the dark matter content of galaxies is a very different physical processes than supernova feedback or agent feedback. At the end of the day, I will say that, galaxy properties probably live in a manifold. They are not really occupy the parameter space equally. They live in a manifold. You can clearly see here that they follow these lines or whatever it is. And this manifold is something that moves with omega matter. And this move with omega matter is very different to what feedback does. And that's why, even with one single galaxy, because you are inside this manifold, you are able to constrain the value of omega matter. This is our explanation.
Yeah. I have to admit, it doesn't really surprise me that there is this manifold. What I think pre-machine learning is that, let me think how to express this. Like, so you have your universe evolving and galaxies are forming in different, pretending that there are different universes with different values of omega matter. Yeah, there's different amounts of total mass. So your initial condition for your galaxy is quite different. People have already done sort of what you're doing here with one galaxy cluster. By weighing a galaxy cluster, exactly. You can say there's this much total mass, therefore omega matter must be this sort of value. And in fact, the cosmological constant or dark energy was kind of hinted at from this exact thing, that omega matter as measured by clusters was too low. And the reason was that there was missing energy density and dark energy. So it doesn't surprise me that a similar thing can be done with galaxies. It's just that because galaxy clusters are the biggest things in the universe and haven't had a chance to lose mass or to collide with other galaxy clusters, they're more pure.
Exactly.
Whereas a galaxy is this, I guess, in your language of manifolds, the galaxy cluster manifold is still kind of in its dimensional space, a very spherical blob perhaps, or a very contained manifold. But the galaxy's parameter space manifold has just been messed up and twirled and all sorts of movement in this higher dimension parameter space. But then this is what machine learning can do, is it just samples and gradually discovers this manifold. So it doesn't actually surprise me that you can do this. Yeah, maybe it surprises me that it was so easy for you to extract plots like this, which is good, right? That kind of show you what the machine is seeing rather than just imagining that it's smart and well done machine. And
I agree. But this, I don't know, Sean. I mean, to me, that it also works for any galaxy, even for dwarf galaxies, is, I don't know, kind of very surprising. And to be honest, I mean, I should not really make any strong claim here. I mean, I'm pretty sure because we have really done a lot of tests that this is probably not a numerical effect, but still, we cannot maybe discard that possibility that maybe somehow, in all these galaxy formation models, somehow the value of omega matter is somewhat there, and maybe a neural network is really learning these kind of numerical artifacts. I don't think it's the case, but
I guess I have maybe two lingering questions then. One is the thing that you guys in CAMELS have always shown me every time I've done a talk. You trained your neural network on illustrious code, worked it on Simba, and it worked brilliantly, and thumbs up, well done. And then the other thing, environmental dependence. Surely like some regions where dwarf galaxies are forming are more massive because they're in a host that is more massive, which I'd have thought would have biased this kind of neural network idea to higher omega matter. But maybe that's the work these other parameters, Z star, R star, and K, are doing to measure the environment and say, okay, I have determined that I'm in a more massive host halo, therefore I need to correct my estimation. Maybe, I don't know. So yeah, please answer both at the same time or one by one or however you wish.
So that's a very good point. So the first question is about this robustness that we always do, right? I mean, if we want to do this with real data, at least at the level of the simulation, if we train on Illustris and test on Simba, it should work. So in this case, it doesn't work. And the reason for this, you can just see from this plot. You can see that this is from Illustris TNG, this is for Simba. These galaxies are very different. And you can also see in the upper plot. The galaxy properties from these two simulations are too different. If you train in one, it doesn't work on another. So, I don't think this is the end of the history. I mean, I still think that there is some way around this, but the model is not robust right now. We cannot really apply this to the Milky Way too.
I mean, at the very, very, very least, you have extracted an observational difference between Illustris and Simba, that the real world is either one, the other, or something entirely different. So that's something that, even if it's not observationally relevant yet, it's already theoretical physicsy relevant.
Exactly. I mean, it's one of the, talking with some experts about this, if these results are true, what this means is that, galaxy properties will live in a manifold, and the manifold move with omega matter. So what this implies is that if you have a simulation where the value of omega matter is wrong, you should never be able to get galaxy properties correctly in the manifold, right? I mean, maybe if you project in 1D the stellar malfunction, you might be able to get, but you should not be able to get all the galaxy properties in the manifold correctly. And this is a kind of a strong implication of this thing.
Yeah. And I guess this is the realm that observational cosmology is now entering, where we'll be measuring stuff sufficiently accurately that we do need to worry about this level of detail. Okay. So then, what about environmental dependence? What about a subhalo that's just forming in a more massive environment? Why is this technique surviving such phenomena?
So that's a very good point. One of my collaborators mentioned that, maybe galaxy properties will also know, the overdensity where you live. If you live in a galaxy cluster and you are a dwarf galaxy, maybe your galaxy properties will be different than if you live in the field. So maybe the network internally is maybe doing something like that, but I cannot really say for sure.
Or maybe that is the 10% lingering.
It could be.
Statistical error that sometimes you're in a void, sometimes you're in a cluster. And
yeah, but I mean, it will be interesting to try to put more variables to see if things improve. And of course, try to repeat the exercise with 2 galaxies or 3 galaxies to see if, I think in principle, it should improve, because you can see that the manifold has some width. It's not a line. So with more galaxies, you will be able to get this manifold much and much better.
Possibly. There was that. Yeah, I'm not sure. It depends how correlated the errors are. The other thing that now is in my mind is two intuitions are clashing with me now. So you showed that within Illustris on its own that you couldn't measure these supernova AGN parameters, which suggests that somehow changing them won't change the galaxy properties that you then use to measure omega matter. Or is that not true? Because then the conclusion was, why does it not work with Simba? If the feedback isn't relevant, why does it?
But this is maybe different, I think, in this case, Sean. So I think, when we change AEN, for sure, I think it will have changes in galaxy properties. But maybe using one single galaxy, the scatter is maybe too large to pick up the change. I mean, maybe agent feedback is changing this, but the scatter is like this. So, the change is not really, you are not really able to see it. So I think it's a slightly different thing in that case.
What should the cosmology community take away from this work? How should we update our beliefs?
Again, I don't really want to make any strong statement here. I mean, if this is true, I think it's important, or at least interesting. And, again, I don't think it's a numerical artifact, but this possibility is still there. But the important thing is that if this is a numerical artifact, this is something that is going to be very important, for there are many people trying to do likelihood-free inference at the level of the field, So you need to be aware that the simulations has these effects, these artifacts, if this is what is going on, because this is information that is not physical. This is a numerical artifact.
What is keeping you up at night about this, and what would you want to discuss with other experts? So it sounds like you've already pre-contacted experts to do sanity checks.
Yeah, so I mean, the reason why this paper it haven't been out like a few months ago, it was precisely because we didn't really understand. And I was worried that it will be a numerical artifact. I think now with this interpretation, I think it's probably not. But yeah, I will definitely like to talk with really experts on, like numerical simulations to see, if there is still room for some kind of numerical artifact about this, or whether this is physical. And if this is really physical, I think it's really, really interesting, right? Because I think this is going to be like a new link between cosmology and galaxy formation at the level of a single galaxy. So this is, I think, it's going to open like a lot of possibilities. So I will definitely love to talk with, galaxy formation people. And
I mean, it seems to me that if you worked on this statistic to the point that it was observationally relevant, there's a kind of very obvious galaxy one has access to measure. And normally it's in the way and annoying for cosmology, but this would make it, like the cosmological playground. And obviously I'm talking about the Milky Way, the one we're in. Thanks Paco for the good work, the thought-provoking work, and the great talk.
Thank you, Sean.
Well, I hope you like that. There will be a live discussion in February or March about this talk and all the other talks in this CAMELS series. If you want to be informed about that, then let me know and I'll add you to a mailing list. There's more CAMELS goodness in a playlist in the description, and a new video every day until all 8 CAMELS cosmology videos are out. So why not go watch one of them? In the meantime, if you want the YouTube algorithm to suggest more videos like this to you, don't forget to like and subscribe, and have a wonderful day.